Hi everyone. This is my first ever year A-level, rather, I'm going to say year 12 stroke 13 A-level live stream. And the reason I wanted to do this one today is because I know that a lot of students have got like either mocks coming up if you're in year 13, or a lot of year 12s have got assessments coming up as well. So what I've done for today is I've picked a number of topics, and the topics that I've picked are going to be topics that are going to be relevant to both year 12 and year 13, but they appear on A-level papers quite a lot as well. Okay, so they're going to be giving rise to quite a lot of marks, definitely. So the first thing I'm going to go through is I'm going to go through something called differentiation optimization. Okay, really, really important technique. And just to say thank you very much to yesterday's maths exam, is the resource that I'm using, because they've compiled a lot of Edexcel exam questions and a lot of exam questions in general by topic. Okay, so they've kind of like compiled exam questions by topic, and it's yesterday's maths exam that have like compiled these questions. So what we're going to look at is we're going to look at differentiation optimization first. Okay, and the particular reason I want to look at this is these questions just give rise to so many marks. I mean, this particular first question we're going to go through gives rise to like 10 marks, but there are other ones that like can give rise to even a lot more marks than that. And they're just so important. And in my experience, students are generally not that convinced, not that, they're not really that sure about what it is that you have to do with these particular questions. Okay, so yeah, just to recap, differentiation optimization, it's suitable for year 12, it's suitable for year 13. If at any point anyone has any questions, then just ask me and I'll be happy to answer any questions as we go through. Okay, perfect. So right, let's have a look at this first question then. Really good question. Again, this is an Edexcel exam question. And what does it say? It says a manufacturer produces a storage tank. The tank is modeled in the shape of a hollow circular cylinder closed at one end with a hemispherical shell at the other, as shown in figure 9. Okay, the walls of the tank are assumed to have negligible thickness, and the cylinder has a radius of r meters and a height of h meters, and the hemisphere has a radius of r meters, and the volume of the tank is 6 meters cubed. Okay, show that according to the model, the surface area of the tank M is given by that particular formula there. Now, for questions of this type, they're all the same. You need to start off by finding an expression for the volume of the tank, okay, to start off with. And then you start off by finding an expression for the surface area of the tank, okay, in these particular cases. And then we kind of like end up substituting one equation into the other in order to find out the expression that they're asking for. So I've started this question by finding an expression for the volume of this tank. Okay, so let's have a look at this, the volume of the tank. So what have we got? We've got the hemispherical shell, which is like half of a sphere. So 4/3 pi r cubed divided by 2, which is 2/3 pi r cubed. And then we've got the cylinder, which is pi r squared h. Okay, so that is going to be 2/3 pi r cubed plus pi r squared h. So we're going to add those two things together in order to find an expression for the volume of the tank. So I've got that expression there, and I'm just going to park that result because we've got an expression for the volume, but it's in terms of r and it's in terms of h. Now, the next step is we need to find an expression for the surface area of the tank. Okay, now let's have a think about the surface area of the tank. So the surface area is going to be the area of the hemispherical shell plus the area of round the side plus the base. Okay, so we've got the base plus round the outside plus the top. And the top is going to be half of a sphere. So half the surface area of a sphere. So that's going to be 4 pi r squared, but divided by 2. So that's going to be 2 pi r squared. And then we've got this is the curved surface around the outside. So that is 2 pi r times by h. Okay, so that's going to give us that area there. And then we've got the base is pi r squared. Now, as I'm going through this, if anyone has any questions, just type them into the chat and I'll endeavor to answer your questions if you're unsure. But we're just doing differentiation optimization, which is suitable for year 12 and 13. And it gives rise to so many marks, and it comes up all the time. I've seen this come up in EdXL, OCR, AQA, they love this example what to do. Right, so let's have a look at this next one. So basically what we've got to do now is we have got the hemispherical shell, which is 2 pi r squared. We have got the rectangle here, which is going to be 2 pi r times pi h. And we've got the base, which is pi r squared h. So when we add all that together, that gives us 2 pi r squared, add 2 pi r h, add pi r squared. So those two combine to give us 3 pi r squared, and we've got 2 pi r h. Now that's our expression for our surface area. Now we've got to try and show that the surface area is given by this expression here in the question. Okay, we've got to show that it is equal to 12 over r plus 5/3 pi r squared. Okay, so what we're going to do is we'll note the first thing to notice is this equation that we're aiming for. Notice that it has no h in it at all. So there is no h in this expression. So what we need to do here is we need to find an expression for h and be able to sub that in there in order to eliminate the h. And the way we're going to do that is from this equation that we got here before. Okay, so we're going to take this equation and we're going to rearrange this to make h the subject, and we're going to sub that in. So let's do that. So we're taking this equation, rearranging it to make h the subject, and we're going to sub in. So let's have a look. So we're going to do, all I've done is taken 2/3 pi r cubed over to the left-hand side, and that gives us pi r squared h. Again, just rearranging this formula from before. We are then now going to divide by pi r squared. So when I divide by pi r squared, I get the expression for h is 1 over pi r squared times by 18 over 3 minus 2 pi r cubed over 3. Okay, so that's our expression for h. And we're now going to sub that into our expression for the surface area. So we're subbing in the expression there for h is equal to 1 over pi r squared. That's getting subbed in for the value of h from the previous equation. So that goes in there. Now this gives us that our surface area is now equal to 3 pi r squared plus 2 pi r times by the expression for h, which is 1 over pi r squared times by the 18 over 3 minus 2 pi r cubed over 3. So we can simplify this now. Let's have a simplify it. So when we expand all of this, that pi cancels with that pi, that r cancels with the squared. And then when we do 2 times 18, we get 36 over 3r. Okay, so that is 36 over 3r. And then here, when we times this by this one, we end up with 4 pi r squared over 3. So we've expanded the bracket now. So now all we've got to do is just collect like terms again. 36 over 3 goes to 12. And then 3 minus 4/3 is 5 over 3. And if we just change the order in which we write it, we can see that we've got the expression that we were after. Okay, so just to recap on what was the process for doing that, we basically wrote an expression. So here's the question so you can see it. This differentiation optimization, we basically just found an expression for the volume, subbed in the fact that the volume was 6. We found an expression for the surface area, and we rearranged this one to make h the subject, and we subbed in there. Okay, and that gave us the thing that we were after, and that's our first 4 marks. Now the next thing, it says the manufacturer. Now in my experience, these part B's are always like way easier than part A. So it says the manufacturer needs to minimize the surface area of the tank. Use calculus to find the radius of the tank for which the surface area is a minimum. So a minimum occurs when dA by dr is equal to 0. So we're going to differentiate this expression with respect to r. Okay. Now notice I've written it as, instead of writing it as 12 over r, I've written it as 12r to the minus 1, just because that makes it easier for us to differentiate. So we times by the power that's there, lower the power by 1, times by the power that's there, and lower the power by 1. And because of the fact that this is a minimum, we're going to set this equal to 0. Okay. So we set it equal to 0 because it's a maximum or a minimum. And then we just solve for r. So I'm going to add that 12 over r squared across to the other side. And then I'm going to times the whole thing. Going to make r squared the subject. We're going to make r the subject rather. So I'm going to times that by r squared, and I'm going to divide by 10 over 3 pi. And when you do that, you end up with this expression, r cubed is equal to 12 times 3 over 10 pi. And when you work that out, that turns out to be 1.0464. And when we write that, we basically do that whole thing to 3 significant figures. Hi, so we've got a question from SV. Am I going to do a year 13 question too? So basically, the answer to your question, SV, is this is differentiation optimization, okay? And this is on year 13, okay? In fact, every question that I'm going to go through in the live stream could be on a year 13 paper, okay? So although it's a topic that is like a year 12 topic, it's one that basically appears on the year 13 papers all the time. And in my experience, most year 13s don't know how to do this question. You wouldn't believe, SV, how many times I do go through this differentiation optimization question where people have no idea. And what I'm going to look at as well, SV, in this particular live stream is I'm going to do 2 other topics that, although they're technically year 12, in my experience, they come up all the time on the papers, and a lot of year 13s are not sure about them. And that is logarithm modeling, okay, and exponential modeling. So that's what I'm going to look at, logarithm modeling and exponential modeling as well in a minute when I've done these differentiation optimization. Because even though they are technically year 12 topics, they come up on A2 papers and they're worth so many marks that I think they make the difference of like almost 2 grades. And I know a lot of people aren't clear about them. Good. I'm glad you're happy about this, SV. So we found part A. We know part B. We've used calculus to find the radius of the tank that has a minimum surface area. Okay. Now, if anyone has any questions, just ask me as we're going through. Now, the next bit, it says calculate the minimum surface area of the tank, giving your answer to the nearest integer. So this is quite a nice, easy version of this one because we found the value of r where this happens. Okay, r is 1.05. So we just sub that value of r back into the original equation, okay, that we found out in part A. So the 12 over r plus 5 over 3 pi times by the r cubed, okay? And that gives us the area. It says give your answer to the nearest integer. So that is 17. Now, this particular question didn't ask us, but sometimes questions of this type ask us to justify the fact that we found is a minimum. So like say, for example, in this next question here, which you can see is worth, oh my goodness, it's worth 15 marks, okay, and could come up on an A-level A2 paper. It says in part D of this question, it says justify that the value that you found is a maximum. Now, when you're asked to justify that something is a maximum, what you need to do is take the second derivative. So in this particular question here, because it's to do with V, we'd find out d2V by dx squared. And if that second derivative was greater than 0, that would mean that we had found a minimum. And if the second derivative d2v by dx squared was less than 0, then that would mean that we had found a maximum, okay? So when they ask you to justify that the answer you found is a maximum or a minimum, you would take the second derivative, okay? And that's what you would do. Now, there's just one more question that I want to look at on this differentiation. By the way, I can't recommend the website enough, Yesterday's Maths Exam. It's an amazing, if you've never heard of that website, I definitely recommend you check it out. Yesterday's Maths Exam. If you go on there, they've compiled loads and loads of exam questions for you to practice by topic, and it's just super useful. So here you can see we've got all of the differentiation optimization questions, and they are very, very useful. It's a great website, great free resource. So I'm very grateful to Yesterday's Maths Exam for this. Now, the second type of question on this differentiation optimization is this one here. I just want to look at this one, and then we'll move on to another topic, okay? So this one, the thing that's different about this one is instead of having a volume and an area, we've got a perimeter and an area. So it's just like a little bit of a variant of that other question, okay? And I think that, yeah, in recent years, certainly in the last year or two for Edexcel, there's been questions more or less exactly like this question have come up on the papers. So it says figure 3 shows a flower in year 13. Figure 3 shows a flower bed. Its shape is a quarter of a circle of radius x meters with 2 equal rectangles attached along its radii. Each rectangle has a length equal to x meters and a width equal to y meters. Given that the area of the flower bed is 4, show that y is equal to that. So let's first of all find an expression for the area of this flower bed. So what have we got? We've got one rectangle there, which is xy. We've got another rectangle there, which is xy. And we've got a quarter of a pi x squared, the whole circle. So we've got 2 times xy plus a quarter of pi x squared. Okay. And then for part A, we've got to just rearrange this to make y the subject. So what we do here is we're just going to, what have I done? I've just times everything by 4. So we get 16 is equal to 8xy plus pi x squared. And then from there, I have subtracted pi x squared and divided by 8x. And we get the expression that they were after in part A. Now, part B, this is where this question's very, very similar to what they've done before. It says, hence show that the perimeter, p meters of the flower bed is given by that equation. So let's find an expression for the perimeter. So what have we got for the perimeter? We have got x add y, add another x, add another x, add another y, add another x, and a quarter of the circumference. So we've got x add y, add y, add y, add y, add x, add a quarter of the circumference, which is 2 pi x. So that comes to 2x add 4y add a half pi x. Now, notice that this equation that we've got here has got x and y in it. However, the thing we're after has no y in it. So we need to take this result from part A, and we're going to use that, and we're going to sub that in there for the y. So you'll notice that the y has been replaced by this expression from part A. So we now get the perimeter is equal to 2x add 4 times 16 minus pi x squared over 8x plus a half pi x. And then from there, all I've done is just literally expand this bracket. So you're going to have 4 times 16 is 64 over 8 pi. 4 times pi x squared is 4 pi x squared over 8x, and so on. And then we can just collect like terms and simplify it. And we find out that we get 64 over 8x is 8 over x. 2x, there we've just got 2x. This simplifies into minus a half pi x, and minus a half pi x add a half pi x, those two cancel out. So we're left with the perimeter is 2x over 8x as required. So that's our part B done, okay, of this kind of differentiation optimization question. Part C, use calculus to find the minimum value of P. So again, we're going to differentiate it and we're going to set it equal to 0. So I found out dp by dx, differentiate it, is going to equal minus 8 over x squared add 2, because it was minus 8 over x plus 2x. Set it equal to 0 and solve it for x. So I've added the 8 over x squared over to this side, times by x squared divided by 2 and square rooted. Now, the reason that I've got rid of the minus is because it makes no sense to have x is equal to minus 2 in the context of this question, because x is a length. So it doesn't have any meaning. So we can ignore the minus. So for part B, we found that the value, for part C, we found that the value of x where it occurs is 2. But what they want us to do is to find the minimum value of the perimeter. So we found it happens when x is 2. So we now sub that 2 into our perimeter equation. Okay, so we get 8 over 2 plus 2 times 2, which gives us the perimeter is 4 add 4, so 8 meters. And I think that's a really nice, really nice 5 marks for part C. And then finally, it says, find the width of each rectangle when the perimeter is a minimum, giving your answer to the nearest centimeter. Well, in part A, we found this expression for the width of the rectangle. So all we've got to do is sub in the value of x equals 2 into that equation. And when we sub that in, we find out that we get y is 0.214 meters. And in centimeters, it says give your answer to the nearest centimeter. And to the nearest centimeter, that's going to be 21 centimeters. Okay, I hope everyone's happy with that question. If everyone's got any questions on that differentiation optimization, let me know. Right, the next thing that we're going to look at is, now I know that, again, students really don't like this. So this is going to be logarithm modeling, okay? And if whether you're in year 12 or year 13, you recognize this kind of question. It's super important. It comes up like all the time. And I know that people are not particularly confident in knowing what to do with this question. Now, there's various ways you can tackle this question, okay? But what I like to do is I like to do it by taking logs. So let's have a look at this question. Let's see what this one's about. It says the resting heart rate, H, of a mammal is measured in beats per minute, is modeled by the equation H is equal to PM to the power of Q, where P and Q are constants and M is the mass of the mammal measured in kilograms. Figure 2 illustrates the linear relationship between log to the base 10 of H and log to the base 10 of M. The line meets the vertical log to the base 10 of H axis at 2.25 and has a gradient of minus 0.235. Find the values of P and Q. So here's my preferred approach. I like to write down H is equal to PM to the power Q. And I'm going to take logs. So I'm going to have log H is equal to log P plus log M to the power of Q. I'm then going to use the power law to bring the Q to the front. So I've now got log H is equal to log P plus Q times by log M. And what I like to do now is I like to write down Y equals mx plus c and rearrange this so it fits the pattern, okay? Now, if we look at the x-axis is log to the base 10 of m, and the y-axis is log to the base 10 of h. So it makes sense that I'm going to say log h is equal to m times is equal to q times by log to the base 10 of m plus log to the base 10 of p. So all I've done is taken this equation and rewrite it in the way that makes sense so it matches the pattern of the question, okay? And we've got here that we've got log m is our x-axis and we've got log h is our y-axis. So that makes sense because that's like our x and that's like our y. Now what that means is that the gradient of this graph is going to give us q, and they tell us the gradient is minus 0.235. So straight away we've got the gradient. And also the y-intercept is going to give us log to the base 10 of p, and we can see that the y-intercept is 2.25. So what that means is that log to the base 10 of p equals 2.25. So therefore p is equal to 10 to the power of 2.25, okay? So that's how we're going to work that out. So we're going to go 10 to the power of 2.25, which gives us 177. So P is equal to, actually, it's going to be 178 if I go to three significant figures. So we've got P is 178, and we've got that Q is minus 0.235, and that's part A done. And that's the way that I prefer to do that, by like taking logs. Now this next bit, which means that our model, by the way, is that H is equal to 178 times by M to the minus 0.235. That's our complete model. Now part B, this bit gets people. People often don't know what to do for this bit. It says a particular mammal has a mass of 5 kilograms and a resting heart rate of 119 beats per minute. It says verify, comment on the suitability of the model. Oh, actually, that bit's not too bad. I can't believe really that that's worth 3 marks. So all we need to do here is just sub in a mass of 5 and see what heart rate that gives us in order to see whether or not the model is suitable. So when we sub 5 into that equation, we get that H is equal to 122. Now, we've got 122 there, and that is not very far out from the actual heart rate, because the actual heart rate is 119, okay? And if we had 119 divided by 122, then that is like 97.5. So it's less than 2.5% out. So we're going to say that it is a suitable model. And as a good rule of thumb, if something's less than 10% out, then we can say that it's a suitable model. Okay. Now, this is the next bit that people don't get. It says, with reference to the model, interpret the value of the constant P. Okay. In my experience, like when I'm teaching this, most people do not know this unless they've seen a question of this type before. So the model is H equals PM to the Q. And the question's asking us, what on earth is the significance of P? And the answer to that question is, if you imagine you've got a mammal that has a mass of 1 kilogram, then yes, SV, you get confused with that part C as well. You're not on your own. Almost nobody, SV, that I ask knows the answer to this part C unless they've seen this question before, okay? And the answer is, if you imagine you've got a mammal that has a mass of 1 kilogram, then the equation would become H is equal to P times by 1 to the Q. But 1 to the Q is just 1, so therefore it would just H equals P. So it's the resting heart rate of a mammal with a mass of 1 kilogram. Okay, so that's what that bit is. Okay, now that's a really important style of question, comes up a lot. The third type of question that I wanted to look at is an exponential modeling question. Okay, again, they absolutely love these exponential modeling questions, and I think they're really nice way to pick up some marks. Okay, so it says this, I like this question. It says the owners of a nature reserve decided to increase the area of the reserve covered by trees. Tree planting started on the 1st of January 2005, and it says the area of the nature reserve covered by trees, A kilometers squared, is modeled by that equation. Okay, so A is equal to 80 minus 45 e to the CT, where C is a constant and T is the number of years after the 1st of January. Okay, so it says, find the area of the nature reserve that was covered by trees just before planting started. Well, when planting started, time was equal to 0. A common error that people make here is they put that A is equal to 80. Okay, that's one common error. But we know it's not going to be the case, because when we've got T is equal to 0, we've got A is equal to 80 minus 45 times by e to the 0, which is 1. So A is equal to 80 minus 45. So it's actually 35 kilometers squared is the answer to part A. So that's part A. Now it says on the 1st of January 2019, an area of 60 kilometers squared of the nature reserve was covered by trees. Use this information to basically find out what the value of C is. So in order to do this, we just need to sub in the information that we've got. So we have got that 60 is equal to 80 minus 45, because now we know that, well, no, that's given anyway, is equal to e to the 14c. Because by 2019, we've got up to a time frame of 14 compared to when we started in 2005. So we can just solve this now. Just add that 45 over there. So 45 equals e to the 14c. That is equal to 20 when we take 60 off both sides. So e to the 14c is 20 over 45. And then we're going to basically now take natural logs of both sides. So we're going to have that 14c is going to equal ln of 20 over 45. And then finally, we divide by 14. So c is 1 over 14 times by ln of 20 over 45. And when we work that out in our calculators, that turns out to be minus 0.579. Now, again, this next bit that we're about to do, it's only worth 1 mark, but oh my goodness, it comes up like all the time, and it's often worth more than 1 mark. And in my experience, very few people get what's going on. So our model now is 80 minus 45 e to the minus 0.579t. Okay, so that's our model. Now we found out what C is. Okay, and it says on the 1st of January 2020, the owners of the nature reserve announced a long-term plan to have 100 kilometers squared of the nature reserve covered by trees. Okay, state a reason why the model is not appropriate for this plan. Okay, so basically what we've got to think about here is the shape of this graph. This is an exponentially decreasing curve. it's e to the minus something. And e to the minus x looks like that, okay? So in other words, as x tends to infinity, e to the minus x is going to tend towards 0. So this long-term model is basically saying that a is going to tend towards 80 minus nothing. In other words, the long-term behavior of this model is that a is going to basically tend towards 80. And so therefore, the owners of the nature reserve are hoping to get 100 kilometers squared covered with trees. This model is inappropriate for that, because basically the greatest area that this model predicts that's going to be covered by trees is only going to be 80. Okay, so this with this model, it's actually impossible to get up to an area of as far as 100. So those are 3 topics that I know come up in year 12 and year 13 that I know that people find really, really tricky. So of the people that are with us, if you wanted to look at some year 13 topics, obviously I'm going to do more of these like kind of like live streams in the future, moving forward, where I will be looking at exclusively like year 13 topics. But anyone that's in the stream, if you've got any particular topics you want to look at that you want me to spend a little bit of time going over, any topics that you're struggling with in your revision, because I'm more than happy. You type it in the chat, any topics you want. I'm more than happy to have a look at any other topics. So in my so basically in my groups, I've got like 2 year 13 groups and I've got a year 12 group. And what we're doing is we're looking at integration in the groups. Okay, so we're just kind of like getting ahead of the syllabus, and because I think like the earlier you can look at integration, the better. So we've finished like the differentiation chapter, and we've done parametrics. We're looking at integration, because I think, you know, some schools teach everything in order and they finish integration just before Easter, but it does not allow you enough time at all to be able to absorb what's going on. So, you know, I'm looking at integration. So SV, you want to do some mechanics. You're struggling with year 13 mechanics, yeah? Maybe integration. So year 13 mechanics, oh my goodness, yeah, we've got some. Let's look at a year 13 mechanics. Let's do year 13 mechanics, and maybe a good thing to do would be the how about something like the inclined plane, SV, something like inclined plane with friction. I don't know how that kind of thing would sound. Let's have a quick look at something like the inclined plane. So I'm going to do that. Let's have a quick look at that. Just going to open up a relevant question to have a practice on the inclined plane, because the inclined plane, that's a really good one for mechanics. So we'll just open that up. Just give me a moment. Let's go to active learn. I don't know if you've done, yeah, inclined plane. That's the worst part. Oh my goodness, SV, no way, that's not good. It's actually, I actually quite like the inclined plane when you get used to it and think about what's going on. So let's just have a quick look at inclined plane with friction. I'm just going to open up. I'm going to use the Edexcel textbook. Okay. So if I just go to, let me just get to the right bit. Just bear with me. I'm just going to open it up. Whoops, I accidentally opened the pure one. Let me just open the correct one. So here's a copy of the textbook, and we're going to go to applications of forces. We're going to do dynamics in the inclined planes 147. Okay, here we go. Let's have a look at that. Okay, so 147 applications of the inclined plane. Now, let's do, yeah, I mean, this one looks like a good one. Let's have a look at this one. Get really confused about get the directions wrong. Yes. Okay, that one doesn't look too bad. I think this one, example 11, looks like a good one. And I think the thing that I often go wrong is like dropping signs. You know, you end up with like so many equations. You can end up dropping signs. So let's look at the inclined plane here. So I'm just going to read this question. Unfortunately, I can't select, you know, without seeing the answers. But the first thing is to get the sketch going, right? So it says a box of mass 2 kilograms is pushed up a rough plane inclined to a horizontal surface by a force of magnitude 25 newtons. The plane is inclined to horizontal of 10 degrees. Given that the coefficient of friction between the box and the plane is 0.3, find the acceleration of the box. Okay, so let's have a look at what we've got. So we've basically got our box, and it's being pushed up the slope by a horizontal force of 25 newtons. Now, that's an alternate angle. So because that's 10 degrees, that means that's 10 degrees there, because they're alternate angles. We've got our weight coming down here, which is 2g. We've got our normal reaction up here, which is r. We've got our line coming here. Now, that is going to be 10 degrees as well. And that is going to be our right angle, okay? Now, because the object's being pushed up the plane, friction is acting in the opposite direction to which the object is moving. So that's our basic sketch, okay? Now, when we've got friction, we always need to resolve perpendicular to the plane, okay? So first of all, let's start off by resolving perpendicular to the plane and see what we get. So we're going to have the normal reaction pushing away from the plane. So we've got R. And then we've got the component of the weight that's pulling the object into the plane. And in this triangle here, that is the adjacent and that is the opposite. So it's going to be 2g cos 10 is the component of the weight that's pushing it into the plane, okay? So 2g cos 10 there. The component of this force that's pushing the object into the plane is going to be 25 times by sine of 10, because that's the opposite and that's the adjacent in this right angle triangle. So it's going to be 25 times by sine of 10. So it's going to be plus 25 sine of 10. Okay. Now they've chosen to write it as cos of 80 in the textbook, but I've just written it as sine of 10 from this triangle here. I hope that makes sense. So that's our equation for resolving perpendicular to the plane. And that's really good, actually, because we know everything when we resolve in that particular, all of that can be worked out. So now let's resolve going up the plane, because the object is being pushed up the plane. Now it's in motion, so we're going to use Newton's second law. So we're going to write down F equals ma. Now let's think about what's going up the plane. So we've got 25 times by cos 10 is pushing it up the plane, okay? Because that's the component of this force that's acting up the plane like that, 25 cos 10. So we've got 25 cos 10 going up the plane. We've got the friction going down the plane, so minus F, okay? And we've also got the component of the weight that's acting down the plane. And the component of the weight that's acting down the plane is 2g times by sine of 10. So 2g times by sine of 10 this is the component here acting down the plane. So that is 2g times by sine of 10, which they've written as 2g cos of 80, but that's the same thing as sine of 10, is equal to the mass, which is 2 times the acceleration, which is what we're trying to find. Okay, that's perfect. So now we've resolved perpendicular to the plane and we've resolved up the plane. So we now just got to replace this F with mu r, okay? So F is mu r, like that. 25 cos 10, and that is equal to 2g times by sine 10 minus 2a. And actually, this looks good now because the question tells us that the coefficient of friction between the box and the plane is 0.3. So that's good. So we know that that's 0.3. We know what this r is from before, so we can calculate what that r is. In fact, let's just work that out now so we can put that in. So r is 2 times by 9.8 times by cos of 10. Make sure I'm in degrees rather. Plus 25 times by sine of 10. Okay, which is going to give us 23.64. So if I write that down, r is equal to 23.64. So we've got 0.3 times by 23.64 there. And then we've got, we know that and we know that, so we can work out what all of those are. So if I just write 25 cos 10 there, and I write minus 2g sine 10 there. So let's work out what these are. So we're going to have 23.64 times by 0.3 gives us 7. That is 7.093. So then we're going to have 25 times by 25 times cos of 10. 25 times cos of 10 minus our 7.093 minus our 2 times by 9.8 times by sine of 10. Okay, close bracket. Okay, that gives me 14. That's looking promising. 14.12. So I get that 14.123 is equal to 2a. And then finally, I'm just going to divide that answer by 2. And I find that I get 7.06. So the acceleration is equal to 7.06 meters per second squared. And so if I give that to two significant figures, that's going to be 7.1 is the acceleration to two significant figures. But yeah, I agree that those questions, those kind of like inclined plane ones, can be really, really tricky for sure. Perfect. Well, I think I might just, but again, yeah, mechanics. You know, I've done quite a lot of work on mechanics in my groups as well, and I am trying to upload more mechanics questions to the YouTube channel as well. In fact, I think I've been through 2025. I've done a walkthrough of 2025 mechanics on the channel as well. So you might find it helpful to have a look there. There should be quite a bit of mechanics questions. But perfect. Well, thank you everyone for joining us there on my first ever A-level live stream. I will be doing more in the future, and I am open. Maybe I'll do like a little sort of poll in terms of what topics people want to do in the future. SV, you've got a question. Let me see what your question says. How do you know when to equal the equation to 0 and when not? Okay, SV, that's the answer to your question is this, right? It depends on whether it's moving. So when we resolved perpendicular to the plane, SV, it was in equilibrium, okay? Which basically means that the forces acting that way equal the forces acting that way. So when I basically resolve perpendicular to the plane, I just wrote that equals that. Now, what I could have written is I could have written r minus 2g cos 10 minus 25 sine 10 equals 0. So the answer to your question there, SV, is you set it equal to 0 when it's in equilibrium, okay, when it's not moving. However, when we resolved up the plane, this force of 25 newtons was pushing the object up the plane, so it was moving, so that's why it was not equal to 0, okay? So you put it equal to 0 when it's in equilibrium, and when it's not in equilibrium, you use F equals ma, Newton's second law, for when something's moving. I hope that answers your question, SV, yeah? But yeah, keep an eye out. So I'm going to be posting more content for year 13 on the channel all the time. I try to add content almost every day to my channel. I will be scheduling some more year 13 specific live streams, and I'll do a little poll as to what topics people want to look at. Okay, so I'll do, if you look on the post, I'll do a poll about what topics people want to look at, and in my next live stream, I'm more than happy to look at anything that people want to look at. Okay, perfect. Yeah, no, I think that well, SV, I only just started my channel not long ago, so I really appreciate your feedback there. I only started it like a few months ago. So I think actually it's grown pretty well considering it's only been going like a handful of months. So, but thank you. And I'm glad that you found it helpful. But keep an eye out. There's going to be a lot more stuff coming up in the future. But I hope you found that helpful, everyone. I hope you have a good rest of your day. And I'll look forward to seeing you in more live streams in the future. See you later, everyone. Thanks a lot. Bye-bye.